Hello everyone, I'm Shuman. Today I'll be talking about dynamic network congestion games. This is a joint work with my thesis supervisors at INRIA Rennes in France. And let me first introduce you to our to routing games, which is one of several models of network congestion games that have been studied in the literature, and we have been inspired from them. And this particular model has been studied by Tim Garden from 2005. So the basic idea here is you have a directed graph as the game arena, and there are a number of players who wants to go from a source vertex to a target vertex, and their objective is to pay optimal cost in the traveling, and each edge is marked by some cost function. The cost function might depend on the number of players. For example, here edge e1 is marked by x, which denotes that a player who takes the edge e1 in their path has to pay the same number as the same as the number of players that takes edge e1 in their path. Here two players are taking edge e1 in their path, so each of them are paying cost 2. Similar is the case for edge e4. On the other hand, there are other edges like e2, e3, e5 which have constant cost functions. So here the total cost is 28, and in each individual player's cost is 7. Now, as I said, the objective of each player is to pay optimal cost. So one red player would like to switch its path from red to yellow one, and reduce its cost from 7 to 6. And some other green player who is now paying cost 8 would like also to switch its cost from 8 to 7 by switching its path from green to yellow, and this can go on. And when a player switches its own path to reduce its own cost, the total cost might get increased, other players cost might get increased, and this behavior of individual players is called selfish behavior, because they only think about their own cost. And um, on the left hand side, the behavior that I'm showing is called centralized behavior, because here as if some external agent assigns paths to the each player in order to optimize the total cost. Now in this kind of framework, selfish behavior may arise in different manner with different individual costs and different total cost. Here, for example, here in the right hand side, the total cost is 36, which is much higher the say total cost here which is 30. Now our main area of interest in this context is to study how this selfish behavior behave compared to a centralized one in terms of total cost, and how bad it can be, how close it can go to the centralized behavior. Now, having introduced the basic structure, I'll now show you on what aspects we differ from the model that I just described. So the first one is synchronicity in the cost computation. So in our model, players bear the congestion effect for an edge only if they take that edge simultaneously. And it is not the case in the most of the model in the literature, where players have to bear congestion effect if they take their edge, if they take some common edge. It doesn't matter whether they take that edge at the same step or not. For example, here the red and the green player, they both use edge e4, but the red players are taking the e4 at their third step, while the green player already at target vertex t. So they do not take the edge e4 simultaneously, so they do not bear the congestion effect due to each other, and this lowers the player's cost, but algorithmically it doesn't alter anything as much as we can tell. Now we also differ on another aspect, which is strategy space. In most of the cases, player I mean in the literature, player strategy have been a path from a source to a target vertex. They do not observe anything. I mean, they do not decide by observing anything about what other players are playing, but the strategies that we are considering are of the form where player can decide, player observe how the history is going for all the players, and at some step it can decide what will it wants to play next depending on what others are playing. For example, here the red player would play the solid red edge if there are less than two players at s1. If there are more than two players at s1, then it will continue to play the dotted red edge. So these kind of strategy we call dynamic strategies, and we consider these dynamic strategy in our model. So in short, our model is, we call it dynamic network congestion game because it is a congestion game played on a network, and the dynamic term is coming from the dynamic strategy. The network is given by a set of vertices, set of edges, and we have k as the number of players and unique source target vertex for all the players s and t. And cost functions are non-decreasing functions given on the edges, and it might depend on number of players. Configurations are k-tuple, and cost of a player is computed as shown in the expression, and it's just synchronous cost function. And the strategies, traditional strategies that traditional path strategies, we call it blind strategy because in that case player do not observe anything and play blindly, and the dynamic strategies are the one where players observe and play accordingly. Now we need to recall some standard concepts from game theory that we are interested in. For example, Nash equilibrium is the one which formalizes the selfish behavior, and social optimum is the one which formalizes centralized behavior. Nash equilibrium is a profile from which no player has an incentive to deviate unilaterally from its current strategy, and social optimum is the profile where the social cost or the total cost is minimum. And price of anarchy and price of stability, which are the two measures given by Kutopea and Papadimitriou in 1999, compares these worst and best Nash equilibria with social optimum in terms of total cost. Now, most of the study in the literature have been around finding bounds for price of anarchy, price of stability for different congestion game model, like linear congestion games with polynomial cost, etc. But we mostly talk about in a different approach. We consider an instance of our model and want to compute price of anarchy and price of stability for that particular instance. So this is another aspect where we differ from the literature. Now the question, as we differ our model from bit, we need to first show that Nash equilibria exist in our model, and that proves the well-definedness of price of anarchy, price of stability for our model. And then we'll delve into details how we compute these measures for our model. So for existence of Nash equilibria, we start with any arbitrary blind strategies, and we ask whether a player has a strategy to deviate, has an incentive to deviate from its current strategy or not. If the answer is yes, we ask what is the best response of that player in the current scenario, and we replace its current strategy by that best response. So this problem we call best response problem, and we continue in this way until the answer becomes no. So when the answer becomes no, that means that there are no players who can improve their cost by changing its current blind strategy. Now this is the definition, by definition this is a blind Nash equilibrium. Note that we only allow players to change its strategy to a blind strategy. That's why it is a blind Nash equilibrium. Now, and these dynamics, we call it best response dynamics. Now, best response problem can be solved for any strategy, blind or dynamic strategy, in polynomial time by a reduction to shortest weighted path problem. But these dynamics only we can show the termination of these dynamics only for blind strategies, not for dynamic strategies. That's why we considered blind strategy. And this proves the existence, this termination proves the existence of blind Nash equilibria. But in fact, we can show that blind Nash equilibria are Nash equilibria in our model. Why? Because if you start with a blind Nash equilibria, if you ask whether, if you now allow a player to deviate to some random strategy and ask whether they have one, and if the answer is yes, then the deviating, because all the other players are playing with blind strategy, the deviating dynamic strategy can be simulated by another blind strategy. So if the answer to the previous question is yes, then we are actually getting a blind deviating blind strategy for the deviating player. But that contradicts to the fact that we started with a blind Nash equilibria. So these kind of deviating strategy cannot exist if we start with a blind Nash equilibria, and that proves that blind Nash equilibria are Nash equilibria. And so that shows the well-definedness of POS and POA in our model. The next immediate question is if we consider dynamic strategy, are there more Nash equilibria, or more interestingly, are there any better Nash equilibria? And the answer to both these questions is yes. If you consider this game arena with 3 players and the strategies that I am showing here, which is red players are playing the red solid path unless at S1 or S2 there are less than 2 players. In that case, they will play the dotted red path, and the green player is playing blindly the solid green path. If you consider this strategy profile, this is in fact a Nash equilibria with total cost 36, and we can verify that any blind Nash equilibria in this game arena has total cost at least 37, which means considering dynamic strategies may alter the price of stability and price of energy. This depends on the strategy space. So our this somewhat shows that our model is effective. Now I'll go into details how to compute this price of anarchy and price of stability in our model. For this, we consider these 3 decision problems called social optimum, based any, and worst any. In all these 3 decision problems, the inputs are same, which is instance of a model and a natural number. And we ask that for the first one, we ask whether there exists a strategy profile with social cost less than the given value. For base training, we ask whether there exists a Nash equilibria with social cost less than the given value. And for worst training, we ask whether all Nash equilibria have social cost less than the given value. Now, after solving this by using binary search, we can actually compute the SOPT, price of stability, and price of anarchy from this decision problem. So let's tackle this decision problem one by one in the next. For social optimum problem, we consider the configuration graph. For example, consider this game arena with 3 players, and this is the configuration graph of that instance, where each vertex is a configuration of the instance, and the edges are marked with the total cost of the transition. Now, to solve this social optimum problem for the instance, we ask whether there exists a weighted path in this configuration graph with total weight less than the value. If the answer is yes, then the social optimum problem, answer to the social optimum problem is also yes, and vice versa. Now, but this configuration graph is double exponential in the input size, because the size of the configuration graph is v to the power k, and k, the number of players, can be encoded in binary because we consider unique source target pairs. So if we solve this problem in the configuration graph, the complexity is very high, so it's a bad news. But we can solve the same problem, in fact, in a much smaller graph, which is where the vertices are not configuration, rather Parik image of the configuration, and solve the exact same problem here. And we have also bound on the length of the path in the graph, so we can just non-deterministically guess a path in this graph, which is exponential in the size. So the problem, social optimum problem, lies in PSPACE. Now, for Nash, now we are going to the details of decision problems involving Nash equilibria. For these problems, we can first characterize the outcomes of any. For this characterization, we consider the unfolding tree of the configuration graph, which potentially is an infinite tree, and each branch from the root node in this tree is essentially a play in the game. And defining a strategy profile in our model is essentially the assigning a branch from each node in this tree. Now we want to characterize a a branch in this tree, and we want to see what are the necessary and sufficient condition for that branch to be an outcome of n. So now consider an arbitrary node of this branch, say row n, and considers configuration C prime, which can be obtained by a single player deviation from row n, say player I deviation. Now if we want to make this branch as the outcome of any, that means it has to be immune to any single player deviation. So that means if player I deviates to C, we have to make sure that whatever it plays, it end up pay more than cost more than it would have played in this suffix. Now how do we know that? So we compute val IC from this configuration for player I, and val IC is the minimum cost that player I cannot avoid from this configuration if uh, uh, if it starts a game here against the coalition of the other player. Now if this val IC plus the player I's cost in this deviation is more than the cost of player I in the suffix, and if it is true for every such player I deviation from row n, then player I doesn't have would not have any incentive to deviate from this configuration. And if we can make sure that such condition holds for all player and for all step of the branch, that means for this branch there is no step, and at no step no player would want to deviate from this branch, and which essentially means this branch is an outcome of Nash equilibrium. So and we can compute this val IC, which will need it in exponential time by a reduction to the value computation of a two-player turn-based game, and it's a reduction into a Congestion's paper from 2008. Now, with this characterization, we develop our algorithm as follows. So, in this algorithm, we essentially guess a play of our model or a branch in the unfolding tree of the configuration graph. While a play is just a sequence of configuration in our model, in this algorithm, along with the configuration, we also keep a counter for each player. We start with the initial configuration and the counter value initialized infinity, and when we guess a path, we update the counter along the way. Now, the update happens as follows. Each time we take the minimum of these two terms. The first term checks if the current transition is taken, whether player I they could have deviated and reduced a cost from history or not, while the second term checks if the current transition is taken, whether player I can deviate and reduce its cost at this state or not. So if these two values are non-negative, that means after taking I mean this current transition extends an outcome of Nash equilibria. And so in the guessing part, but we always want this mi positive for all the players I, and this guessing stops when we reach the target vertices for all the players. Now let's look at one such example. For this game arena and three player, we make a guess where all the players are taking this transition, but the counter value is negative. So we terminate this guess and start a new one. And in the second guess, say we the guess is okay, and when we try to extend it, we see that the one of the counter value is negative, so we stop this guess and start afresh, and so on and so forth. So when we when we have a play which where the all the players are at the target vertex, we have identified a play which is an outcome of Nash equilibrium. But we do not want any outcome of Nash equilibrium, rather we have specific condition for our decision problem. For the there exists any problem, we also keep the total cost in a counter, and at each point we verify that whether the value is still less than the given value or not. For all any problem, we do it by storing with the negative value and checking at each step whether the value is less than m for all or not. If the answer is yes, then the answer to the decision problem is no, because we have identified a path with total cost greater than m for all. Now we can do with this negative weight, because in this path there will be no cycle, because the counter value always decreases. Now we do not store the whole path, rather we only store the current and the next configuration at each step, but it still need exponential space, because the configuration takes mod b into k, and k is exponential in the input size, and we have a bound on the length of the path for both for both the there exist and for all any problem, which can be encoded in in exponential space, so the overall algorithm is exponential space. Now uh, up until this point we only talked about Nash equilibrium, and that ends our decision problems that we proposed. Now we'll look at the another equilibrium solution, which is subgame perfect equilibrium, which is better suited for dynamic framework. Let's see why. If you remember this example that I showed earlier, there we considered the strategies, the red player strategy as follows: as if they were trying to punish another red player, and this kind of strategy profile would arise in our, if we consider Nash equilibria, but this is kind of unreasonable threat that one player was posing to another, because primarily their objective should be only to go from S to T with optimal cost. They would not want, they shouldn't want to increase some other player's cost. But if we consider Nash equilibria in the dynamic network, dynamic framework, these kind of non-credible threat arise, and to avoid these non-credible threats, we consider subgame perfect equilibria, which is Nash equilibria, but which is Nash equilibria not only from the initial game, but from every sub game. It has to be the strategy profile has to be a Nash equilibrium. Unfortunately, we do not know whether in our model SP always exists or not. Nonetheless, we can ask the still the same question, when we're given an instance of our model and a natural number, whether there exists an SP with social cost bounded by the input. Now, to solve this question, we again characterize the outcomes of SP now, but the crucial difference is in the characterization of any, when a player deviates from the deviating configuration, rest of the coalition of the rest of the player could somehow punish this player by a play on which the condition was only on the cost, but now that punishing, there is a more condition on the punishing play, it has to be an outcome of SP, because outcome of SP, and this is the difficult part of the characterization and developing an algorithm from it. So it is a technical, very technical, and it is out of the scope of today's talk, but the algorithm is heavily inspired from this paper, where the same problem has been studied but for turn-based reachability game. And for turn-based reachability game, the one of the advantage is SP always exists, and it can be shown by a backward induction, but that is not true for concurrent game, which is our setting. So we had to adjust accordingly. To conclude, let's recap. We introduced a model of network congestion games with synchronous cost computation, and we posed a few decision problems and solved in some complexity. We don't have a matching lower bound complexity result for this decision problem. So our future objective is to compute matching lower bound, and the one major problem that we are currently investing right now is to take the number of players in our model as a parameter, and how the price of anarchy, price of stability grows with this parameter. And would like to know more about subgame perfect equilibrium in our model, whether it exists or not, and long term objective would be to study other than reachability, like regularity, etc. Thanks. See you on December 16th and any day during the week in gather.town.